Today we're going to be solving a problem that deals with the topic of resonance. So this idea of resonance is all about our inability to show what 3D molecules actually look like on 2D paper. So if we could draw what a molecule actually looked like in 3 dimensions, we would have no need to talk about resonance because we'd actually be able to see what it looked like 3-dimensionally. However, because we have to draw things to communicate with one another on paper, and we need to use 2D drawings to do that, resonance is our way of explaining in 2 dimensions how molecules actually look in real life. So as we start to solve this problem, one thing that you want to make sure, especially as you're starting out drawing organic compounds and showing electron movement, is to make sure you know where the lone pair electrons are. Just for ease of viewing, I'm not going to put those lone pair electrons actually into this diagram, but make sure that you're able to do that as you're drawing it on your paper. For instance, the oxygen in the C double bond O in the top left corner, that oxygen has 2 bonds, both part of that double bond to carbon, as well as 2 lone pairs that are not drawn. So make sure you keep those kind of things in mind. The nitrogen on that same molecule has 2 bonds and 2 lone pairs because it's in its negative state. And if you have questions, you can refer to the formal charges article. So notice that in these 2 drawings, we've got a negative charge on the nitrogen in the left drawing and a negative charge on the oxygen in the right drawing. And also we can see that there's been a double bond in different places in those 2 drawings. So remember, this idea of resonance is saying that both of these 2 diagrams, both the left and the right drawing, are contributors to the overall definition of what this molecule looks like in 3D. We just have to use these 2 different resonance forms because of our inability to really show what things look like in 2D communication. You can see that the lone pair on nitrogen, the extra lone pair that creates the negative charge, in the left drawing we can show an arrow taking that extra lone pair on nitrogen and forming a bond between that carbonyl carbon and nitrogen. So that's the double bond you can see over in the left drawing. If we did that, however, the carbonyl carbon would now have 5 bonds, so simultaneously we'll need to relieve one of those double bonds up onto the oxygen. That's now leaving a lone pair on oxygen, making the oxygen in the right-hand drawing have 3 lone pairs and 1 bond, which is in its negative state if you go through the formal charge calculations. So that shows the electron movement. But how do we explain which of these 2 drawings would be the major resonance contributor? In other words, the best definition, or the most stable of those 2 forms. So in order to do that, on this article you should have seen a few ranking characteristics of different resonance contributors. And these skills are really important because they're really just helping you determine which of these compounds is more stable, or more likely to exist. So if we look at these 2, the major difference appears to be where the negative charge is located. On one compound the negative charge is listed on the nitrogen, and then on the right compound the negative charge is listed on the oxygen. So as that's the major difference between the molecules, it would be probably most helpful to figure out which of those 2 atoms would like to retain or hold a negative charge most. So this is an easy concept that you guys are probably familiar with, even from first year chemistry, is electronegativity. Electronegativity is basically the desire for an atom within a molecule to draw electrons toward itself. So based on the electronegativity table, which we know fluorine is the most electronegative, and then anything to the further away from fluorine is less electronegative. Based on that, we know that oxygen is closer to fluorine and should be more electronegative. So in this case, we know that oxygen is more electronegative than nitrogen. And that's the reasoning why the compound on the right would be the major definition, or the major resonance contributor. So that's one example, and we can see how we're using electronegativity, which is a really basic concept, to predict which of two compounds is more stable. So if we look down at the second example, now moving down a line, we can see a very similar type problem. We're comparing again two resonance contributors. They differ only by the movement of pi electrons, or lone pairs. So if we want to show how electrons move, just like we did in the top problem, we're going to try to see how the electrons have shifted from the two resonance contributors. In general, you can always follow the flow of electrons because they'll go from the area of high electron density to the area of low electron density. So if we're looking at this example over here on the left, this example, you can see the area of low electron density, means it's missing electrons, is that carbon with a positive charge. So if that's where the electrons are missing, where are the electrons kind of more dense that we could push over to that area where they're less dense? Based on what you see in the diagram on the right, you can see that the oxygen ends up with a positive charge. And we know that oxygen has two lone pairs, which we may be able to use in sharing across this resonance diagram. So in the drawing on the right, we see that one of oxygen's lone pairs has been taken away because of that positive formal charge. So we can start there and see that one of those lone pair electrons could move into a double bond between that oxygen and that carbon. Again, forming that double bond would cause the adjacent carbon to have 5 bonds. So we'll need to take that double bond, meaning the 2 pi electrons, and move it to the adjacent single bond. By doing that, again, we cause the carbon to have 5 bonds, so we'll need to relieve the double bond into the adjacent single bond. So by doing that, we now have added a double bond to that terminal carbon that had the positive charge, and now that carbon has 2 bonds to the next door carbon, 2 bonds to hydrogen, and should be neutral. So notice that when we're drawing these electron movement arrows, the electron pairs moving, we can either draw them from one bond to the adjacent bond, or from an atom to the adjacent bond, or bond to the atom. So it has to be only to the adjacent bond or atom directly connected. That's the only places that we can show electron movement. So we've shown electron movement. We've shown how these two different definitions, only by shifting around those delocalized electrons, how those two different definitions can exist. So now let's pick which of those two definitions is more important. Remember, they still both define this molecule in 3D space, but we want to pick which one of those is the most important. So in this case, if we use the same reasoning we did in the top example, we would see a positive charge on carbon and a positive charge on oxygen. In that thinking, we would say, well, oxygen is more electronegative, so we'd rather have the positive charge on carbon. Which is true from that extent, but in that list of important ideas to consider from stability standpoint, more important than having a charge on an appropriately electronegative atom, more important than that is having all of the octets full. And you know that's an important thing because that's one of the primary reasons that atoms come together and form bonds, is they're allowing sharing of their valence electrons so that they fill up those valence shells. So we want that octet full. So looking at these two diagrams, the one on the left, where carbon has 3 bonds, does not have a full octet. That carbon with 3 bonds only has 6 valence electrons. Whereas on the right, we can see everything in this drawing has an octet. Even that oxygen, which has a positive charge, we can see the oxygen has 3 bonds and 1 lone pair. That's still 8 electrons, even though it has a positive formal charge. So based on the octet rule, we would predict that the compound on the right is the more important resonance contributor, because it's better to satisfy the octet rule. Moving down to the next example, we've again got the same kind of problem, just a different extension. So in this case, I'm going to move a little bit faster since we've gone through this now. We want to show how electrons are moving. We want to go from an area of high electron density to an area of low electron density. And if you look at the two resonance drawings, it becomes easy to see that the nitrogen with a positive charge is the area of low electron density. It's just short electrons. On the other side, where the nitro group is, the NO2, that's kind of a high electron density area. You can see a couple negative charges there that could clue you in. So if we wanted to show electron movement, it's going to start near the nitro group and move toward that positively charged nitrogen that I have the arrow drawn to. So we're going to take one of the lone pairs on oxygen, and it will go into a bond forming a double bond between that oxygen and nitrogen, as you can see on the right hand drawing. So now that that new bond's been formed, we're going to have to show kind of a relief of the electrons from the nitrogen to the carbon in the ring. And then again, the carbon that now has a newly double bond formed, we can relieve it by drawing the pi electrons moving into another pi bond. And then finally, the electrons in the carbon to nitrogen double bond can fall back into a lone pair on nitrogen. That now makes the nitrogen neutral. So looking at these examples, the octet rule is filled on both. Again, you could go to every single atom and convince yourself that each atom has 8 electrons shared in its valence shell. And that would be a really good exercise to do if you're struggling with this. So each structure, left and right, has octet rules. Notice that we've got pluses and negative charges on both nitrogen and oxygen. So putting the most appropriate charge on the electronegative element, that doesn't really seem to be maybe as crucial. But notice one important rule on the article above is that you want to have the least charge separation possible, which basically just means you want as few charges as possible, and if you do have to have charges, you want them to be close together. So of the two, you notice that the left-hand drawing has 4 charges, the right-hand drawing has 2 charges, and those 2 charges are close together. So the right-hand drawing, again, would be the most likely resonance contributor, or the most stable of these two drawings. And again, that reasoning is least charge separation. Then finally, the last drawing, very similar to what we've done before. We're looking for electron flow. You can see in the left-hand drawing there's a negative charge on the carbon. On the right-hand drawing there's a negative charge on the nitrogen, so we need to show that flow of electrons. Notice though that I can't just take the electrons on that carbon and draw it over to the nitrogen, because you can see that there are double bonds in the left and right hand drawings that do not represent each other. So we can't just show electrons moving from one atom to another unless that describes the entire resonance process where the electrons are sharing. So in this case, our carbon lone pair could move onto this adjacent double bond that you can see represented on the right-hand drawing. The double bond above that can move into the adjacent bond, forming a double bond there, as seen in the right-hand drawing. And then finally, because we again have formed too many bonds to that carbon, we're going to have to take the double bond and put it into a lone pair onto that nitrogen. Now that nitrogen has two lone pairs and is a negative charge. So of these two, which one would be the major resonance contributor and why? So notice everything's got a octet full. Again, you might want to go through that yourself, but we have a negative charge on a carbon versus a negative charge on a nitrogen. Just like the example at the top, we know that nitrogen is more electronegative than carbon, and because of that reasoning, we would predict that it's more stable for the negative charge to be on nitrogen than carbon.